video series, we will be learning how to do VLSI with the open source VLSI with the help of cloud because many students have problem in getting Linux on their PC. Actually, putting dual Linux on dual boot is bit tougher. But if you want to learn open source VLSI, you can use cloud also. So these days you can do open source VLSI with the help of Google Cloud and GitHub Cloud also, but Google Cloud has some limitations that it need a paid version for bigger designs. Uh, but in GitHub Cloud you can do bigger designs also, but it needs lot of uh, work to do, like you need to create lot of YAML files and then do GitHub actions. But if you are just a beginner and want to learn um, RTL to GDS with the help of simple designs, so Google Cloud is very good. So now let's get started. So first of all, we will be learning Librelane today. So Google Cloud. So actually, Librelane was earlier OpenLane. So OpenLane is an open source physical design tool developed by eFabless. So now it have migrated to Librelane. So we will be learning how to um, use Librelane on cloud with running a simple design called a serial parallel multiplier. So first of all, there are two ways you can install Librelane. One is with the help of Nix and Docker. So here we are using Nix. Nix is actually a dependency we need for installing Librelane. So first we will running test. So now when we are running this, so let's go ahead and understand things further. So um, we have in now next step is to install Librelane. So we have imported the latest version of Librelane. We have imported the PDK root, and now as you can see, we have installed Next here. Now we will be learning this. So I will be including this link to this GitHub, this Google Cloud collab link on the description of this video. As we are seeing here, Librelane is installed, so we will check the version. We will import Librelane first and check the version then. And then as you can see here, now we have created the Verilog file. So now as this is cloud, we are doing this lab on cloud. Um, so we do the write file spm.v. So it creates a Verilog file in this directory as you can see here. And all the content of this SPM file is exactly written in the file. You can see our SPM file is created in the directory, and the content inside this is exactly same what we have written below this. So now we will configure the design. So if any one of you have worked on OpenLane, so you must have remembered that we need to configure the flow. So first, we will be importing the Librelane config API, as you can see here. So this config is used to define design, PDK, timing, and tool options. So let's learn how it works. So we have defined the top module SPM and the PDK. It is the technology node we have specified. Then we have specified the PDK, the Sky 130A PDK, and it determined the cell standard cell libraries, design rules, timing parasitics, and routing layers. And next is the clock port. So this is the clock input port in the RTL which we have written. So this is the clock input port which we have written. And next we define a clock net name. So it is the internal clock net name after synthesis. So it is often the same as the clock port, but can differ in advanced designs. So this all these settings, the parameters we use for clock resynthesis, timing analysis, clock routing constraints, and next is scale layout. So next we define the tool which we will be with which we will be viewing our GDS. So we will be using KLayout for that. Now next we have successfully configured our design. Now next is the running the implementation steps. So the now as we have defined created our Verilog file, now we will be doing the synthesis. So let's understand how the synthesis works. So we will be importing the step library from Librelane. So it is used in synthesis. So we will be using the step dot factory dot get dot synthesis. And breaks the ASIC flow into discrete steps like synthesis, floor planning, CTS, and everything. So each step is a Python class with inputs state in and output state out. So it is registered in a central step registry. So this lets you run, inspect, or replace step individually. So there are two ways to obtain a step. So Librelane gives you two APIs to get the step class. So one is the direct import by the category. So so here Yosys is the category or the module, and synthesis is the specific step inside the category. And next is the registry-based lookup. So Step Factory is a registry and Synthesis the step ID. So Librelane looks it up and returns the step class. So why steps have IDs like Synthesis? Um, so the ID format is the tool and the step name. This is the tool and the step name. So we here we are using Yosys as the tool. So we have specified Yosys. So this makes steps globally unique, easy to reference dynamically. And then next is now we will run the step and then we run the synthesis flow. So we have imported the synthesis and we have and whenever you are want to learn that how different commands work in Librelane, so you can run the display underscore help command. So as you can see here, it have given the different kinds of synthesis commands which can be used in Librelane. and its type and its description is given. So when you're going to do some advanced design, so these commands will be useful. So based on the design, all these are defined. Next is the synth. Now we will be doing the synthesis actually. In the synthesis step, we convert the RTL to the gate level netlist. So gate level netlist is the combination of standard cells and the connections. So now we do the synthesis. We have defined our Verilog file and the state. So we have given the input Verilog file and it contains a top module. So since the synthesis is the first step, there is no prior data to this. So we pass the empty state here and we start the synthesis. So our synthesis is in progress. As you can see, we have got the number of wires, numbers of memories, and everything is given here. The AND gates and everything, all the synthesis data is displayed here. Now we will be displaying synthesis. So yes, this is done. Next is the floor planning. Now next we fetch the floor planning step using the open. So openrow.floorplan is the registered step ID. So this step is responsible for creating the physical canvas of the chip. And why OpenRoad? So OpenRoad handles physical design tasks such as floor plan, placement, CTS, and routing. So now next is the we what is state in here? So state in is here is so the synthesis dot state out contains the gate level netlist, standard cell information, logical connectivity, and timing constant. So floor planning needs the synthesis output to know how many cells exist, approximate area, power around requirements. So you cannot floor plan without synthesis. So basically, we are getting the output of synthesis and giving to the floor plan to run the further steps. So now we will start the floor plan. So our floor plan is successfully done and we display the floor plan. So this is our floor plan and next we do the tap or end cap cell insertion. So after floor planning, as you can see, we have the chip boundary, the placement rules, standard cells are not yet placed. So standard cells are not yet placed, so before placing the logic cells, the flow must insert mandatory physical only cells, so which are required for process reliability and DRC connected. So these are the end cap or tap cells. So this step inserts them automatically. So end cap. So these are the special cells placed at the start of each standard cell row and end of each standard cell row. And why they are needed? So the end cap cells are proper. So end cap cells properly terminates the power rails, diffusion wells. It prevents the well spacing violations, the diffusion DRC errors, and a broken power rails at the edges. So the key point is they are not functional logic; they are purely physical safety cells. Next is the tap cells. So tap cells connect anywhere to the VDD and the P substrates to ground. So why tap cells are critical? So, if balls, wells, or substrate are left floating over long distance, so the parasitic bipolar transistors can form. So, this can cause the latch up, which results in the cell gets stuck at high and refuses to switch back to IO to LO. So it can permanently damage the silicon. So tap cells prevent this by regularly anchoring the wells to power or the ground. So foundry define a maximum allowed distance between the tap cells. So now we will be the same thing which we have done in the floor planning. We have got the step. We we import the open road for the tab and cap insertion, and we get the previous state, the previous output of the floor plan, and insert to the end cap insertion step, and then we run the flow. So this is our end cap insertion and tab cell insertion. Next, we do the IO placement. So now we need to place the inputs and outputs to it. So we will do that with the same step, same way with which we did the floor planning and cap cell insertion. So this is how you can see here. We have the inputs and outputs placed here. Now we will be generating the we will be creating the power distribution network. So So this is the power distribution network as you can see here. So what does the command do here? So we have uh, so now we import the state which we have kept from the IO placement, and then we define the width of the vertical power stripes. And next, we define the horizontal power stripes as you can see here, the width of the horizontal power stripes. And next, we define the distance between adjacent vertical stripes. And next, we define the horizontal pitch, which means the distance between the adjacent horizontal straps. So we run this command. So we forward to our IO placement is done now. We will display the IOs, and then we run this command, and we run the display. As you can see here, our PDN network is created here. The next we do the global placement. So this video is just for understanding how to use Google Cloud for RTL to GDS. If you want to learn each step in detail, you can comment in the box, or you can also go through the NPTEL lectures to learn about these in more detail. So this is the global placement which we will do here. So the steps are same as what we did in the floor planning and everything. So now we run the global placement. We display the global placement here. As you can see here, all these are all these cells are scattered and we need to place it properly. So for that we do the detailed placement. So as you can see now, our cells are properly placed. Here all this were scattered and now it is properly placed, and now we do the CTS. The same steps apply here also. Our block key synthesis is in progress. So as a part of Chipmunk, we also post the detailed notes also on these things, the CTS and everything. So you can check out our LinkedIn page also. So you will find the notes for each step very detailed. So our CTS is done. We display the CTS and this is done. Now we do the routing. So routing, it lays the wires between two gates. Uh, it so global routing is in this we plan. It should plans the routes the wires between two gates will take. So the result of global routing are stored in internal data structure and there is no effect on the actual design. So in this we are just planning. There's no act. We won't be making any changes in the our layout in this step. So now we will move to the detailed routing. So now we have done the planning for the routing. So in detailed routing, we it guides the global routing to actually create the wires or the metal layers and connect the gates, making the connections finally physical. So we run the same steps, same way which we have used in above steps. So the tail routing is in progress. So it's done, and now we will display the detailed routing successfully done. Now fill the empty gaps with the in the fill insertion step. So we prioritize the use of decoupling capacitor cell to which supports the PDN network. But when there are not any enough cells, we just use regular fill cells. Now we will run the fill insertion. Now we move to the parasitic extraction or the resistance or capacitance extraction. So when we were doing the placement now, before the placement and routing step, so there the nets are no longer ideal wires. After the placement and routing, the nets are no longer ideal wires, so they have resistance which causes the delay or the IR drops. It also causes the capacitance which causes loading, and the coupling capacitance which uh, impact on the crosstalk. So important thing is that RCX does not this step this RCX steps does not modify the layout. It only measures and models the physical effects of routing. So why this is required? This step is required. So So the before PNR, we were assuming the RTL or estimated wire loads. Now, after PNR, we will be considering the real metal lengths, the width, and the layer, and the spacing. So without RCX steps, so the final STA is uh, is optimistic and it's unsafe. So the output of as the output of the step we get the spef file. So spef is also known as standard parasitic exchange format. So SPF contains the net resistance, ground capacitance, coupling capacitance between the nets. So Librelane generates this. So we use the same format of the commands we just used before. Now we do the STA, the static timing analysis. And the last is the stream out. So we finally generate the GDS. Or GDS is generated. And next we do the DRC. So DRC helps in ensuring that the design is actually manufacturable. There are no so for example, if there are not in it ensures that things like if there are not enough space two between two wires or there's too much space between the tap cells, so it helps in ensuring that these things are corrected. So a design not passing DRC will be rejected by the foundry. So who so they also run the DRC on their side. So now we run the same format and next we generate the spice for the LVS. And last is the LVS step which we run. So now we have learned how to do the GDS with the help of Google Cloud. In the next video, we will be learning how to use the GitHub Actions for the GDS flow. So these videos will help you learn the physical design flow without Linux on your PC.